All right, welcome back to System Software. So we are going to start wrapping up our compiler portion of the class with our last component, which is on how functions are implemented with the compiler. Functions are probably the trickiest part because while the machine has arithmetic, it doesn't have anything like a C-like function with function local variables that supports recursion. We basically just have branching. But before we get into that, so we just finished up pointers last time, and I know that's like a very confusing part of C, and that's a very confusing part of the architecture. But questions on pointers, or questions on CoGen 2, which is the pointer exercise, or questions on CoGen 1, which is due today. Questions, questions on anything, logistics, something like that, yeah.
Just to clarify, we're not touching the reference function, we're just saying them empty?
For CoGen 1?
Yes.
Yeah, exactly. Yeah, for CoGen 1. So, maybe I should update this table. But, if it's not in this list, we won't give you test cases that will exercise those functions. And that's true for all the projects, because you don't want, if you make a mistake on CoGen 1, we don't want that to make it so CoGen 3 won't work. So only the functions here. So, the compiler can support all of those functions, but we're going to give you test cases that only trigger those functions in the input. Yeah.
And one more question.
Yeah.
For the overall CoGen project, are we having to make or download a new CoGen CPP file?
Yes. You'll start. Yeah. Yeah. You will. So you'll make a completely fresh repository for each project. So and you'll see it with CoGen, like CoGen 2, for instance. You'll see here that the local repository will be in a different folder. The directions will make a new folder. We'll have you make a new folder, and you'll re-download the compiler template for every project. It'll be a fresh compiler template every time. So the hard-coded, that's why, you treat them all like individually. So for CoGen 2, you'll hard-code these functions again for CoGen 2. You can certainly copy your CoGen 1 if you wanted, but I wouldn't, if you have any errors in it, you could mess things up, I guess. Probably not, but treat them all as separate projects. This is just so that you won't, be penalized multiple times for the same mistake in one project. All right, other questions on,
Are we going to combine all the CoGen projects?
No, you don't have to, but you certainly could. You could take CoGen 3 and then copy in the functions you wrote for CoGen 1 and 2, and then you'd have a complete compiler for simple IR. In the past, I've had students do this, but it's kind of unnecessary because once you get the 3 right, together it'll work. It'll work. So, yeah.
If I can ask, I saw on the schedule there was a project review in there. Is that like a final project or just reviewing?
This is just a kind of buffer space in case there were hurricanes or things were slow. We'll see how fast we get through functions. Functions are probably the more complicated part of the compiler, so we may just continue going over functions here. It might just be open, questions. This was like a very quiet hurricane season for Florida, at least. So last year it was pretty bad. So I kind of like to leave buffer space, but we've been very much on track in this course, so it may not need it. But if there's anything you'd like to go over more, we can do that in this. Or if functions take longer, which they might because they're tricky, we can do that here. Other questions on pointers, arithmetic, CoGen 1, CoGen 2? CoGen 3 is also released today, so it's going to look very, very similar. The main difference is you have to implement all these functions that were hard-coded previously. So they were hard-coded to just have the assembly for one particular IR file. Now you'll have a compiler that will take any simple IR function and generate the assembly code for it. I will go over today, starting today, how to actually generate code for functions. Other questions? Yeah. No, we don't. Yeah, there's no class Tuesday. What's today, Thursday? Veterans Day, yeah, Veterans Day. This is a UCF. If the UCF calendar says there's a break, so there's no classes that day. if I'm not mistaken. So yes, no class on Tuesday. Yeah, no classes, so yeah. Enjoy your break. All right, other questions? Questions? All right, let's do the homework. Finishing up pointers. All right, so if the variable t1 has an offset of -40 from the base pointer, write x86-64 assembly code that will retrieve the value. This is, I had to edit, I had a typo here. Retrieve the value of t1, store it in RAX, and then store 11 into the memory address held by RAX. So what simple IR function is this? What's that? Well, simple IR. What simple IR function is this like? Well, it's one of the equals. There's like several. There's like 4 different assignment operations, or 3, but 4 different assignment operations. Any takers? We went over it last time in the last lecture. All right, maybe let's maybe do the assembly first. What does the assembly code for this look like? Let me bring up some. All right, so if variable t1 has an offset from -40, how do we retrieve the value of t1? Yeah, so we'll move what? -40. Yeah, the RBP thing, and we'll move that into RAX. So now we've taken whatever value was in the memory address given by this operand and put it into RAX. Yeah.
Is the RAX supposed to be $, or?
Oh, I'm sorry. Yeah, percent. It should be percent. So the AT syntax. All right, and then it says store 11 into the memory address held by RAX. So how do we do that? Yeah, we move again. Yeah, $11. Wow, everybody's like reading out assembly experts. Yeah, and how do we put in the address held by RAX? Parentheses. Yeah, good. Parentheses. RAX. That's that register indirect move. Yeah.
Like last time, weren't we saving 11 to like RBX?
Yeah,
And then,
we did.
because that's how I did it.
That's fine. If you, it would, so I don't actually specify what registers to use for this, so it's also equally, was this your question as well? Okay. You could do this, you could also do that. That would be totally fine. And that's what my compiler does.
Do it this way, right?
What's that?
You prefer to do it this way?
I have my compiler generate code that way because it's the same code generation no matter whether this is an integer or an operand.
Yeah.
But both of these, all right, I should do the full program. So both of these snippets of assembly will result in the same state, at least the same user visible state, like functional state of the machine. So they're equivalent programs in terms of their inputs and outputs, if that makes sense. So there's, as you probably noticed in like Python and C, you can write the same program many ways. Yeah. And so yeah, these are both equivalent ways to do the program. So if this is the input and this is the output, then these two programs are functionally equivalent. That is, they have the same input and output. Of course, in this one, RBX is going to have a different state than this one. But all right, questions on this? So what's simple IR if we know that -40 is the offset for T1? What simple IR operation might this? Okay, x colon equals T1. So this is, any other thoughts? Any other guesses what operation this might be? Say again? Okay, asterisk T1. Oh, x equals asterisk T1. Any other guesses what it might be? So if it were x equals t1, let's say x had, well, what's the last instruction for x equals t1? We have some move of something into x's offset from RBP. That will be the last instruction for an assignment to x, right? And we don't even know what the offset is. We know it's not negative 40. So it's some other offset. So it can't be equivalent to this, right? Because it's not assigning x. And that's true for this one too. Although the ampersand asterisk is kind of close, right? Because we're using this register indirect addressing. So there must be some kind of pointer operation going on here in simple IR. That's the only way to get register indirect offset. So I guess by process of elimination, yeah, there's like one other. Yeah, go ahead. Yeah. So good. You're assigning to the address that T1 points to. You're assigning 11 to it. That's what this code corresponds to, because we're taking the value of T1, or the number that's in memory at the location associated with T1, putting that in RAX, and then we're storing into that address. That's a pointer, right? The pointer is taking some value of a variable and treating it as an address. So this is taking the value of a variable by its memory by whatever its memory location is, and then this operation treats it as a pointer. So yeah, good. So it's this. That's this one. All right. Other questions on the homework or on pointers, pointer operations? All right. Let's do attendance. Okay, so let's learn how functions are implemented in the compiler and in the architecture. So, okay, so this is where things are going to get a little bit more confused, even more confusing, I would say, because there really is no equivalent to simple IR or C-like functions in assembly, and we really got to keep in mind that we're translating to assembly. We're not trying to run anything here. So. We can translate a function that's never being called. We can also translate calls to functions without knowing their definition, just like when you write a C program. And we're just doing the translation. We're not trying to execute the program. And so we're going to have to generate assembly code that's going to give us the effect that we want from our function. So I'll build this up slowly, and let's just start with what is a function. Informally or intuitive, what are functions in a programming language, or in C, for instance? What is a function? Yeah.
It's just a specific set of code you can call by name that you can pass specific parameters to.
That's pretty good. Yeah, that's like, I don't know if you looked ahead to my slide, but that's pretty good. So it's just a sequence of instructions you call by name, and it takes inputs and outputs. Yeah, that's pretty. Anybody else have a definition or more to it, less to it? There are other, there are formal definitions. There are other views of functions in other programming languages. So it's any other thoughts on functions? Does that about capture it? Oh, okay, that's pretty good. Yeah, so it's called the function abstraction because the machine doesn't have functions. It's kind of a language tool that you can use to encapsulate a computation. So these are just the polysyllabic words, computer scientists use to describe these. But it's really just like a sequence of instructions that you can call by name. And this is like probably one of the first abstractions that you use in your, when you learn programming. It's probably one of the most common ones as well. So it allows you to substitute computation for a name. You can take a name and you can call it repeatedly. I don't know what that sound is, but you can call the same piece of code repeatedly over and over and over. And because it can take parameters, you can define what the inputs are. That function will have different behavior depending on what its inputs and outputs are. It's almost like a little mini program by itself, or a little mini machine by itself that you can just call by name. Questions, thoughts on the function abstraction? bless you. I think everybody's written functions. I think you've all used them without thinking about it. But yeah, so this is like the first abstraction. It's kind of the first like higher level language construct that really doesn't exist at the architecture level that we're going to create through our translation from the compiler. All right, so let's look kind of intuitively what the behavior, the fancy word for that is semantics, the semantics of functions is. So if we have let's say a function f calling function g, so function f calls g, we call f the caller and g the callee, and f is a function that has some sequence of computation. We run that code instruction by instruction, and when we see the function call, what happens? Well, control transfers to G's sequence of instructions. We pass parameters to it, and G executes. It may call other functions, it may have loops, until it gets to the end where it returns control and a return value back to f. And once that return happens, f continues running right after that call, as if nothing ever happened, as if function f just kind of froze, waited for g to finish, and then f continues running. Questions on that? Thoughts on that? Any disagreement on semantics? Any other thoughts? Pretty straightforward, right? I think you've all seen these. All right, so that's the behavior of functions, kind of intuitively, and the function doing the calling, the function that has the call in it, is called the caller, and the function being called is called the callee. Now, f is not always the caller. There might be another function like main that calls f, and then in that case, f is the callee and main is the caller. Excuse me. Okay, any questions, thoughts? All right. All right, so this is what function calls look like in IR, not assembly, I should say IR. This is what function calls look like in IR, or IR language. To perform a function call, you always have to assign it to some return value. All functions in our language take one or more, zero or more integers and return an integer. So without any parameters, this is how you do a function call. You say call f, and you assign its return value to some variable in the calling function, the caller. And this is like the simplest definition of a function you can make in simple IR. You just say function f and end function at the bottom and return some number or variable. So this is like the minimum you need for a simple IR function, is to define a function. Questions on this? Question on the syntax and the meaning of the syntax in simple IR? So very close to C, just slightly different syntax. Questions on this? Everybody good? All right, so let's take a look at what x86 provides for what look like function calls. So it's very similar to what we see in simple IR and the C language, but as we'll see, it has slightly different semantics. But operationally, if we just want to do a single caller callee in assembly, this is how we do it. We give a label for the function that we want to define. So that's just like for branching. You give a label, right? You want to branch to that label. So at the x86 level, one way to view it is just a label, a labeled section of code that you jump to. In some sense, that's what a function call is in assembly. We'll see it differs a little bit. So we just use a label for the function. And we have a special opcode called call in the x86 world, which will jump to f. And another opcode called ret for return, which will return to the point where we called f. And then for return values, by convention in the x86-64 world, and this is just a convention that's used by the Unix toolchain that we're going to use, the return value is stored in the A register in RAX. So this is just a more convoluted way of saying this, where we call f here and save its return value by copying RAX into the retval address. And for the definition of f, we just have a label that says where f starts running, and we move that 5, that was our return value, move it into RAX and return. And that will effectively pass the parameter back to f. But notice there's no actual movement of that data. We just store the result in RAX, and the caller is expected to know that that value should be in RAX. All right, questions on this? So this RAX is just a convention. It's called the ABI, the calling convention for executable files. And it's the standard used by all of the tooling that we have in the Unix world that we're going to link with. Okay, so call and return, they do a little bit more than just branching. Because notice, if this were just a branch, what would happen when we get to return? How would we know to branch back? So return is like a branch back to call, but how does it know where to branch back to? So what happens is when you do the call opcode, it's really just shorthand for two separate other ops in the x86 world. The first thing it does is it saves the return address. So in this case, the return address is the next instruction after the call. It saves that return address, and then it does a branch. Basically an unconditional branch, just like a jump instruction in x86. And then return does the opposite. It retrieves that return address and then branches back to that address, does an unconditional jump back to that address. With me so far? Did they show this in computer organization? Yes, no, yes, they did. They showed function calls. Maybe, yes, no, no. I don't know if thumb down would mean no or bad. No, they didn't show it. Okay. Yeah, I expect they might not have showed it because this is really more for like supporting programming languages. All right, so let's go through an example of what this will look like at the architecture level when we perform this what looks like a function call. Okay. So how does the architecture know, from computer organization, how does the architecture know which instruction to execute next? The following one from what? How does a jump operation work, or a branch?
Jump operation goes back to the beginning of the loop until it returns no.
Well, okay, so I'll tell you the answer. There's a special register called the instruction pointer, or the program counter. You remember this from computer organization? Program counter? So you've got your code written in memory. So there'll be a move instruction, there'll be a ret instruction, call instruction, another move instruction. And these are in memory as well. These are in RAM. So they have addresses in memory. And the way the machine works is that there's a special register in the x86 world. It's called the instruction pointer, or the R, or the IP. Perhaps creepily named RIP for the 64-bit, which we'll see abuses of the instruction pointer later when we look at software security. But it's called the instruction pointer, the IP. And whatever you put here, so if you put 3 here, that's the next instruction that the machine is going to run. So if you can modify this instruction pointer, you can tell the machine where to start running. And this is effectively what the loader does. The loader just tells, this is what branch does. Branch just alters the IP. That's how branching works. So if you have a branch instruction here, and you say branch 1, well, this is not x86, but if you have a branch instruction here, really all that does is it just does like a register copy immediate load, register immediate load into the RIP, and then the machine's kind of algorithm, this fetch, decode, execute cycle, just looks at the instruction pointer for the next instruction, executes it, and then increments the instruction pointer. The branch instruction just overwrites the instruction pointer. Make sense? That's how like branching and stored programs work at the architectural level. Yeah.
By default, does the instruction pointer have stuff in it, or it needs to be called like?
No, the instruction pointer is a register, so it just has a number. It just stores a number. It's actually a pointer.
So if you have like no calls to other stuff, would it just go down?
Yeah. So the machine will. That's just like the fetch. Did you guys learn like the fetch, decode, execute? I'm like not a computer architecture person, but you probably heard about the fetch, execute, decode cycle, where the architecture will go out and get the next instruction, and then decode it, and then like run it through its circuitry to actually compute the state update. But it's really just a pointer. It's a pointer just like RBP was a pointer. It's a pointer into memory. But in the same way that the machine doesn't know whether the data here is an op or a pointer or an integer. If the RIP is pointing to this place in memory, the CPU is just going to get that from memory and try to run it as if it's an opcode. It'll treat it as an operation, and try to run it. And if it's not a valid operation, like if you accidentally branch into the heap or the stack, your processor will be like, I don't recognize this op, and halt. Kind of like a seg fault if it can't access the memory. Okay, so that's the instruction pointer. The instruction pointer just keeps track of which instruction to process next. And without a branch instruction, the architecture will just automatically increment this. It'll read an instruction, execute it, and increment the instruction pointer. So that's how, this is like 80 years ago, how stored program machines were invented. So originally you had to kind of like program the machine by hand, put in all the instructions, or had to like maybe run them one at a time. But the stored program architecture was like automatically reading through a sequence of instructions for you. And that allows you to do branching, because then you can just change the instruction pointer to do control flow, to jump around the set of instructions. Okay, so that's the instruction pointer. So in this example, we're starting on 3. So this is a system-dependent thing. In the Unix world, to have an executable program that's used by the loader, you have to give a special label called the start label. And so it's kind of like main at the system level. And this is system-dependent and also configurable, but in the kind of standard Linux world, if you have a start label, that's where your loader is going to jump to start executing your program. So once the loader loads this program, it's going to set the instruction pointer to be 3, because that's the start label of this program. With me so far? So this is like the main. We're starting executing on line 3 here. All right, so what does call do? Call saves the return address. So what's the return address here? What's the next instruction that should run after F finishes? Which instruction? Yeah, 4. Yeah, good. So all the call instruction does is it takes RIP, and so it saves somewhere, which we'll talk about in a second. It saves somewhere. It actually saves it in memory. It takes the RIP and adds one instruction to it. In this case, it's just one number. Stores it here, and then it branches to wherever F is. F is instruction 1. So how do we branch? How does branch work at the architecture level? So if we're calling F, and F is instruction 1, how does branch change the state of the machine? Yeah, it just updates RIP to 1. So that's what the call instruction does. It just computes the next instruction, the address of the next instruction, saves it, and then branches to the label that you like to branch to. That's it. Very simple, right? Two very simple register update or state update operations. And then execution continues, so the move operation executes. And in this case, the move operation will set RAX to 5. And then we see the return instruction. What does the return instruction do? Just the opposite of the call instruction. It pops or takes this saved value and updates the RIP to be that saved instruction. That's it. Retrieve the saved address to jump back to, and update RIP to branch to it. Questions on this? Make sense? And now we're executing the next instruction after the call, bless you. And this will, save the return value into the memory location associated with, I think it was called retval. So there was, a memory location here for retval, and now retval will have that return value saved. Questions on this? This sort of makes sense? So at least this kind of function call is pretty simple at the architecture level, right? It's just a branch plus you save the return value. And that's it. So that's how you can architecturally do this conceptual idea of having saved named program state or named sequences of computation where you kind of pause the execution of one part of the program, jump to another, and then go back and continue executing that program. All right, with me so far? Questions on this? Okay. All right, the problem is, what if we have multiple function calls? Is this scheme going to work where we just branch and go back? What's going to happen if we have multiple function calls? Well, the problem is now we have multiple return values that we need to keep track of. And so the solution to this is to keep track of all of these nested function calls in a stack. So this is where, if you ever heard of the call stack or a Stack Overflow, like stackoverflow.com, this is the origin of that term. So the stack is what stores state for the function call. So let's see how this works on an example where we have two nested function calls. So we've got a move instruction, return instruction, call, return, call, move. Here is start, here is G, and here is H. Now the stack is that, we learned several lectures ago about the layout of memory. You've got the heap and the stack, which I think you also learned in computer organization. The stack goes downward, and the stack is used whenever there's a new function call. Space is allocated for that function. So let's put our stack here. And we'll still have our instruction pointer, and we'll use RAX here as well. All right, so what's the entry point to this program? Which instruction, how does the instruction pointer start when we load this program? What instruction is the first instruction? 5, yeah, because the loader in our system treats start as the entry point of the program, and that's what's it's gonna branch to when it loads this program in memory. All right, so we start here on line 5, and the first thing we have is a call to G. So how does the state of our machine change? So what call really does is it pushes the return address onto the stack. So what's the return address here? In this example, when we have a call from instruction 5, what's the return address? 6. Yeah, it takes whatever the current instruction pointer is, adds 1 to it, and then pushes that value onto the stack. And the next step is to update RIP to be the address of the callee, which is instruction 3. Questions with me so far? All right. So now we've got another call, a call to H. And so how does the state of this machine change when we have this second function call? Pushes It pushes the return address. Remember, the return address is the next is RIP plus 1. That's the return address, so it pushes that to the stack. So this is the return address for start. This is the return address for G. And then it performs the branches to H, which is address 1. You see that? Questions on this? So now let's see what happens when these function calls unwind. So we jump to instruction 1. Then there's no other branches. It's a move instruction. So the machine will increment RIP to be the next instruction, instruction 2. And now we have a return instruction. And so what does return do? It pops the most recent value off the stack. So it takes 4, pops it off the stack, and updates the instruction pointer with the value it pops from the stack. And so now, what does that mean? We get back to here. We go back into the code that was associated with G. That's also a return instruction. Same thing happens. We pop 6 from the stack, use it to overwrite RIP, and that puts us right back into start, which can then execute, and then the program ends. There'll really be like an exit function here, but questions on that? Does that kind of make sense? So this is the origin of like the call stack. This is why we call it a call stack, or you have a stack overflow. You have unbounded recursion. Whenever you do a recursive function call, usually there's a new stack entry for that. So if you have unbounded recursion, you're going to fill up your stack, you get a stack overflow. All right, questions? Yeah, I see lots of head shaking. This is good. I think everybody's getting the idea. So this is how, under the hood, you can have nested function calls while only doing branching. So the kind of beauty of this is we have a very simple architecture. We just have registers and memory. We don't have named functions or block code. This is how you can effectively simulate the behavior of nested function calls, even though we just have a straight line sequence of code with branches in it. We can simulate the behavior of these simple IR or C functions. Okay, so the wrinkle here is how do we deal with function local variables? So it's all well and good that now we can do nested functions. What happens when we go to try and do recursion with this scheme of nested functions? So we know recursion will work because, this is a factorial function. This is the definition of it. We call it in main, and it's the classic recursive definition of factorial. So factorial calls itself. But in this scheme, that's really easy, right? Because you just branch to it, basically. You just save the return address and branch to it. And if you have recursion, you're just going to keep saving the return address, branching, save the return address, branching. But okay, so let me walk through this code first, just to make sure everybody's on the same page. So we have a function called fac. We've got this local variable fac n. If n is less than or equal to 1, we return 1. Otherwise, we do this slightly different version of factorial, but I'll show you there's a reason for this. We save the old value of n, we decrement n, and then we call factorial on the new version of n, and finally multiply that saved n, which is the original n, by fac n minus 1, basically. With me on this so far? So it's a slightly convoluted definition of factorial, but you'll see why I wrote it this way in a second. But any questions on this implementation? Classic factorial. You've all seen factorial, right? It's like every teacher uses it all the time. All right. So let's see what happens when we go to, and now we have our saved n as a global variable here. So it's just going to be saved once in memory. So let's see what happens when we go to run this program. Okay. So we call fac of 3. Uh-oh. So we call fac3 in main. So here's main. And then inside main we call factorial of 3. Inside factorial of 3, which branch do we take? Do we take the n less than or equal to 1 branch or the other branch, the else branch? else branch, right? Because fac is 3. So here, saved n is set to 3, right? And then we update n and we call fac on 2. Because we do n equals n minus 1, so we call fac of 2. With me so far? Questions on this? When we call fac of 2, we again enter the else branch and we update saved n to be 2. We do n equals n minus 1 and run fac of 1. And now when we're in factorial of 1, we trigger the base case, right? We trigger the if branch, so that returns 1. So fac n of 1, you can think of it as, well, let's just write return 1. So we return 1, and where do we go back to? We go back to the call of factorial of 2. And the next line in factorial of 2 is multiplying this return value, fac n. So it multiplies fac n times saved n. And, oh, that's ugly, asterisk. It multiplies fac n by saved n. What is fac n? That's the return value from fac 1, so that's 1. What is saved n? That's 2. So great, we get fac of 2 returns 2. And now we're back inside of which function call? Fac of 3, okay. Hopefully you're following the recursion here. So we're back inside of factorial of n here. So we're back inside factorial of n. So the next instruction is to multiply factorial of 3, that version of fac n, times saved n. Well, what is fac of n? That's the return value of fac of 2. And what's the value of saved n at this point in the program? Who says 3? Who says 2? So remember, it's a global variable. So every time we wrote to it, that was written once for the whole program. So the value of saved n here is 2. The value of saved n here is 2 because of this assignment to saved n. We assigned saved n to 2 here in this call to factorial of 2. Because remember, it's global. It's a global variable. So whenever you set it, it's set for the whole program, for any execution of that program. And that is not correct, right? That's not a correct implementation of factorial, because what do we get as a result here? We get, we return 4. And that's not a correct implementation of factorial, right? You see that? So why does this happen? Or what needs to change here in order for this program to work correctly? Or like, yeah, can you think of like, how might we change this program? I mean, there are lots of ways. What's that? What's that?
Get rid of the global variable.
Get rid of the global variable. Well, now we saved n will break. So yeah, we get rid of it. Well, what can we do with that global? What's that? Make it local, yeah. If we make this a local variable, then the program will work. Why? Why will the program work? I don't expect you to know it, but the reason is because these local variables, global variables, are allocated once in memory for the whole program. Local variables are actually automatically allocated every time you call the function. And you don't see this in C, but in order to have function local variables, to have correct recursion, these function local variables, they need to be reallocated every time you call the function. So this global variable is allocated once for the whole program, once for every definition of fac. There's one definition. But with the stack, we can allocate a fresh copy. It's kind of like making a fresh version of this function every time it's called. And this is what enables recursion to work. Now, if we had not made a fresh copy of this and we just did a kind of plain assembly translation of this, we would end up overwriting saved in. We'd end up overwriting all of these local variables accidentally by all the calls, because what is function call at the architecture level? It's just branching. But we need more when we want to have we want to have recursion. Recursion is really like creating a new copy of this function for each call to it. Okay, so here's how we store function local variables. We also use that stack, that same stack we use to store the return value. We can also use that to store the function local variables. And by having function local variables, so here's the updated version of it. I just moved saved in into the local variable. What this means is that in C, there's actually a keyword called auto that is the default for function local variables, and it means automatically allocated state. So every time this function is called, fresh memory is allocated in that stack for that function call, for each call. So then when we get to this point in our program, when we get to this program here, instead saved in will be 3, because each instance of saved in will have its own memory location for it. Whereas for global variables, it's just a single memory location for the whole program. And then we'll get, the right value for factorial. Okay. All right, so let's see all right, questions on this? I know that was maybe a lot to digest, but I think people were following along, so that's good to see. All right, so let's see how we manage this local variable allocation. So remember, we're not going to be evaluating these functions. We have to generate assembly code that's going to do this for us. If we just have call and return at the x86 level, that doesn't do any kind of variable allocation for us. It just does branching. So it's going to be the same if we just allocate one memory slot for the entire program for these local variables. We're going to have the same kind of behavior we saw with these global variables. So how can we, at the assembly level, allocate space for these local variables? And we do this using the stack. And there are special operations for managing a stack. So just like there's a special register for local variables, RBP, there's a special register for the instruction pointer. The architecture provides special instructions specifically for managing a stack. So this, like language support for function local variables, heap and stack, this is supported at the architecture level. The designers of this designed the architecture so that it would support language implementation. All right, so in the x86 world, we've got a special register, RSP, which is a pointer to the top of the stack. And we have two opcodes, push and pop, which push and pop to the stack. So it works, very much like the stack you learned about in CS1. A couple of idiosyncrasies. The stack grows downwards in memory. That is, the bottom of the stack is the high memory address. And then when you push, the push, just like with call, there's push and pop can be decomposed into simpler architecture operations. So push just subtracts from that stack pointer and then copies whatever data you're pushing into that new address. Whereas pop does the opposite. It copies the data out of that address and then adds to the stack pointer, which pops it off the stack. So just visually, this is typically drawn when we draw these memory diagrams. When we see memory diagrams, typically we put the high address here at the top and the low address at the bottom. And RSP, SP for stack pointer, if RSP has this address, is pointing at this address, when we do a push, it increments RSP so that it points to the next address, and pop adds to the address to pop it off. So if RSP is like address 10, when I do a push, then we increment it to address 9. When I do a pop, it adds 1 to it to put it back to address 10. All right, questions on this? Push and pop? Okay, so to quickly allocate space, this is and I've given you code for this already. This is the local variables function. You've already been using this. The local variable functions basically just subtracts from the stack pointer. So we could just call push repeatedly for each local variable that we have, but a fast way to do that is to just directly subtract from the stack pointer. So in this case, if we've got 2 8-byte local variables and the stack pointer is here, if we want to allocate space for 2 variables, say this is at address 32, and we want to allocate space for 2 local variables, 16, that's 16 bytes, we want to have a slot here for X and a slot here for Y. Well, we can just subtract 16 from the stack pointer. So now the stack pointer points here. With me? Kind of makes sense? And this is how local variable allocation works. So whenever the function, at the very beginning of the function, the very first thing we do is we update the stack pointer to allocate space on the stack for our local variables. And if we do, and because this is the first thing that runs whenever this function is called, if this is a recursive function or called by another function, the very first thing that happens is space gets allocated in memory for its local variables. And then at the end, once the function's done and it no longer needs that space, we just add to the stack pointer to deallocate that space. Questions? Questions on this? All right. All right, and then each of these spaces we just allocate, we just associate with one slot in memory. Now, how do we access those variables at runtime? Do you remember what assembly operation we did in order to access, say, X? How did we access local variables? Remember? RBP, right? We use the special register RBP. So the way this works is, let me start fresh again. So if RSP is here, and we want to allocate 2 variables, X and Y. So this is address 32, address 24, address 16. To allocate the space, we just update RSP by subtracting however much space we need for our local variables. That's going to move RSP down. But what we do is before we change RSP, we set RBP, another register. We use a register to save the beginning of the local variables. So we save those local variables first in RBP, and then we allocate the space by updating RSP, the stack pointer. And now look what happens if we do that. If we just first take whatever the original value of RSP is and save it into RBP, after we move RSP down, now our local variables are just offsets from RBP. That kind of make sense? Kind of bring full circle how variable allocation works. So we start here on the stack, and there may be lots of function calls before us. We save whatever the current stack pointer is into RBP. That gives us, for this function call, like a fixed location in memory that we know by looking at RBP. We may not know the actual address when we're compiling the program, but we know that it's going to be in the RBP register at runtime. And then we just assign, in the compiler, we assign offsets from RBP for each variable. And so even though we don't know the actual address of these variables at compile time, we as the compiler writers just allocate fixed offsets from RBP. So that when we go to use variables, we can just generate this offset from RBP, this instruction to move and store data to and from this memory location using register indirect offsets. Kind of makes sense? So what we did as a compiler writers, we took something that we don't know at runtime and we turned it into something that we do know that we don't know at compile time, and we turned it into something that is always true for every execution of that program, something we do know at compile time. So no matter how other functions get called or how this memory is allocated or where the system gives us memory, we set up an invariant, something that never changes in any execution of the program, so that X will always be an offset of -8 from RBP. We arrange our assembly code, we plan our assembly code so that that will always be true for every execution of the program. And that way we can guarantee that when we generate our code, it will behave as we expect. It will always use this memory location for values of X in our translated program. Make sense? Questions on this? Okay. All right, so that's called the base pointer. It holds what's called, and so this allocated memory for the function call is called the stack frame. Let me see if I actually get to this. This is called the stack frame. We'll look at the whole. We'll get to the whole stack frame next week once we get into like parameter passing and all that. But here is the assembly code kind of structure of any function call that you'll see. And you'll see this if you actually translate, like if you look at compiled code in the wild, and people are into like reverse engineering and malware analysis will be very familiar with this. You'll see you have a label for the function name. You have code that saves the stack pointer, sets the base pointer as the current stack pointer. And then code that allocates space on the stack for local variables. And then once the body of the function is done executing, we remove those local variables from the stack, and we're going to actually like update the base pointer as well. Okay. So yeah, this is actually what I just went over, that we record offsets from the base pointer here. Let me see. Try to see what to get into next. Oh yeah, okay. All right, let's go over this part. This will make clear how to use it. All right, so any other questions on how the memory is allocated? And this also is where this symbol table comes from. So the symbol table is these offsets from RBP. So yes, these are a little different. So in our compiler, we're also saving a register. I'll get into that when we talk about the application binary interface. So the symbol table will look -8 more than what I show here in class. But I'll explain that next time when we get into the calling convention. Okay, so just to kind of review, now that we see how memory is allocated for function calls, when we have a memory store like this, where we're asking 1 to be assigned to X, and we want to implement that on the architecture, these are our move operations. So we've got move 1, so immediate load of an integer into a register. That doesn't do any memory access, right? That just moves it into a register. If we were to move into RBP, that would just overwrite RBP. So we need to do this memory indirect addressing. And because RBP is like the beginning of this set of local variables, and each variable is assigned an offset from it, we use this array index like this, indirect memory offset addressing to store into local variables. So that's just like where this comes from. I just sort of told you had to kind of believe that this is how you access variables. This is why we access variables this way. Okay, yeah, there's the offsets. So if we have this is where enter assign comes from. If we have an instruction like this is the assembly. We save whatever the right-hand side is into RAX, and then we move RAX into the offset from the base pointer. Questions? Questions on this? All right, let me see. Well, we have 6 minutes left. Let me see what I have time. Yeah, okay. Let's just finish up this part. It'll just be a little review. Yeah, okay. Let me do this example showing what happens, not at the assembly level yet, but showing what happens excuse me, on the stack when we call this function. So let's say we call example variables. Remember, what does the call instruction do in the assembly level? What does the assembly call instruction do?
Change the RP.
Yeah, it would change the RP, but what does it do first?
Saves the next one.
Saves the return address, yeah. So when we have this call, the first thing that happens is the return address is, sorry, not the red val. The return address is saved onto the stack. And then we branch into the function. What's the first thing that the function does? It allocates space on the stack for its local variables. So RSP will point here, RBP will point here, and now we can generate code here that will, update the state of these the memory locations associated with X and Y. So that's kind of half of the so-called stack frame. So this section of memory is called the stack frame. So for each invocation of a function, this chunk of memory is allocated automatically by the assembly code generated by the compiler to store all the information we need in order to run the function, give it its local variables, and also return back to the caller. All right, so I think, yeah, okay, I'll just show the assembly code for this. So the first thing that happens is we save the base pointer, so that saves it at what the original stack pointer was when we entered the function. We allocate space for the local variables, and then here are the instructions that you saw from CodeGen 1 and the assignment. Save the return value, that's stored into RAX by convention, and then we remove these local variables, restoring the stack back to where it was before we entered this function. Okay, let's leave it at that, because then we've got, well, actually, yeah, let's leave it at that. Let's see, we only have 3 minutes left. We went over a lot, so. All right, everyone, have a good weekend, have a good holiday, and we'll wrap up functions next week or the week after. All right, everyone, take care.